Hello everyone, welcome to the next lecture of the Machine Learning Teach by Doing project. In this lecture, I have taken the ambitious task of trying to explain the neural network architecture in 30 minutes. The reason I'm trying to make these small videos is so that you can have a quick recap before going for interviews, so that very quickly you will brush up all the concepts in a lot of detail. So let's get started on this journey. First, I'll be explaining the building blocks of a neural network, and second, I'll put all of these blocks together. There are no prerequisites required, and I'll try to explain every single thing from scratch by writing it down here. So, first, let me start with the first building block, which is called as a neuron. So, just like when you're assembling Lego pieces, you build blocks together, right? A neuron can be considered to be the smallest building block of the neural network architecture. And at its simplest function, the neuron does this. It is represented by a circle like this. It takes an input and then it gives out an output. That's it. The reason it's called as a neuron is because when people started thinking of these concepts, the idea was to model these according to the biological brain. And the neurons in our brain also work in a similar manner. They take an input and then they produce an output. That's why it's also called as a neuron. So the function of a neuron is that it takes an input and then it gives out an output. That's it. Now you must be thinking what these inputs are and what these outputs are and what really happens within the neuron itself. So inputs are the features which will be used to make a prediction. Let's say we have measured three properties: the ear flappiness index, the pupil length. So let me write the problem down. Let's say the inputs are x1 is the pupil diameter, x2 is the ear flappiness index, and x3 is the whisker length. These are my measurements, and the output is whether it's a cat or whether it's a dog. So the whole aim of my neural network, which I'm trying to construct here, is that it should take in these three features. It should take in the pupil diameter, it should take the ear flappiness index, it should take a whisker length as three inputs, and then it should output whether it's a cat or whether it's a dog. For the purposes of this demonstration, let's look at a neuron and its input, its output, and what happens within. So, as I mentioned, the neuron, let's say there are three inputs which are there: x1, x2, and x3. These will be the three inputs to the neuron. So, this neuron has three inputs, and every input will have a weight associated with it. So, this is called W1, this is called as W2, and this is called as W3. The reason these weights are there is because they give an understanding of how important that particular feature is. So for example, if W1 is way higher than W2 and W3, it kind of informs that this neuron places a lot of emphasis on the pupil diameter, for example. So these are the three inputs to the neuron, and then we have an output. Let me call this output currently as F, or rather let me call this output as Y. Now, what happens within this neuron itself? This is where the magic happens. So, after we take the inputs and after we assign the weights, let's see what happens within this magic itself. So, let me zoom in further here. So, the neuron essentially has three important features or three important functions which every neuron performs. And let me represent these three here. The first function which a neuron does is the summation operation, which is the summation. The second function which a neuron does is adding a bias term. And the third function, which is probably the most important function which a neuron does, and that's called as the activation function. So, whenever you hear of the term neuron, remember that it does three things: summation, bias, and activation. Mathematically, what this looks like is that it takes in this input features, it takes in the weights, and it first of all does the summation. So, it does um, W1 x1 plus W2 x2 plus W3 x3. Then what it does is it adds the bias term, bias, and then what it does is it takes the activation function. So f of w1 x1 plus w2 x2 plus w3 x3 plus b. This is the function, or this is the output which is given by this particular neuron. So you see how these three elements are coming together here. This is the summation, this is the bias, and this entire thing is the activation or the activation function. So every neuron in a neural network does these three functions. It takes in an input features x1, x2, x3. It assigns weights to it, w1, w2, w3, and then it produces an output y, which is equal to f of w1 x1 plus w2 x2 plus w3 x3 plus b. So there are three operations happening inside a neuron simultaneously. There is a summation operation, there is a bias operation, and then there is the activation function. Out of all these three things which are happening inside a neuron itself, the summation and the bias term are pretty straightforward because they showed up in regression and classification also. The main thing, which is the true power of a neuron, comes from the activation function. And there are several activation functions which are typically used in every neuron. And I'll have a separate lecture on that. But just to give you an example of the overview of the uh, activation functions, ReLU is a very common activation function which looks something like this. For negative values of inputs, it's 0, and for positive values, it's just equal to x. So its function is max of 0 comma x. Another famous activation function is the sigmoid. And remember, the sigmoid assigns probabilities to events, so it looks something like this. And the mathematical form is 1 upon 1 plus e raised to minus x. Now consider our example where we have these inputs and we want to classify whether it's a cat or dog. Essentially, we want to assign probabilities, right? So sigmoid is an amazing activation function. So what we can do is we can take the sigmoid, and then if it's greater than zero point 0.5, we can say that it's a dog. If it's less than zero point 0.5, we can say that it's a cat. Why zero point 0.5? Because the sigmoid crosses 0 at y equal to zero point 0.5 over here. So if we use the sigmoid activation function, let's say, then the output of this neuron will become sigma of w1 x1 plus w2 x2 plus w3 x3 plus b. So let's take some random values. Let's say w1 is 1, w2 is 1, w3 is 1, and let's say x1, x2, x3 are 1, and let's say b is equal to 0. So if we take these random values, then for these values of weights, the output of this neuron will be sigma of 3. And if you look at this function, sigma of 3, which means it will be somewhere here. So it's on the positive side, so it's greater than zero point 0.5. So since it's greater than zero point 0.5, then we'll say that it's a cat. Because in our notation, we said that if it's greater than zero point 0.5, it's a cat. If it's less than zero point 0.5, it's a dog. So this is how a neuron operates. Remember that we do not know these weights currently. We do not know what is W1, what is W2, what is W3. And that is the main purpose of training or optimizing these neural networks. We need to find these weights so that the answer matches well with our training data and also the testing data. But right now, I showed you the main function of the neuron. So this is the first building block of a neural network, which is the neuron. Now let us look at the second building block. So you might be thinking that, okay, what is so special in this? Because if you look at this thing, sigma of W transpose X plus B, this actually looks just like a logistic regression, right? Where also we had a sigmoid activation function. And there also we were classifying whether if it's greater than zero point 0.5, it's in one class, and if it's less than zero point 0.5, it's another class. So what's so powerful about neural networks? The real power of the neural networks comes from the second building block, and that's the layers. So layers is just stacking this bunch of neurons together, and that is where the true expressivity of neural network comes into the picture. So when we think of layers, we stack a bunch of neurons together. So let us see how this stacking actually looks like. So let's say these are my inputs again, x1, this is x2 and x3. And now instead of one neuron, I will have three neurons. So this is neuron number 1, this is neuron number 2, and this is neuron number 3. Remember, inside the neuron, all of these will be doing the same three things. All of them will be doing the summation, bias, and the activation. So all of them will have these three things which are happening inside, and all of them will have an output associated with it. But let us look at the weights. So as I said, every neuron places an weight to the inputs, right? So if you look at the first neuron, there will be three weights, and those will be W11, W12, and W13. These are three weights. Now, if you look at the second neuron also will have three weights associated with it. Those will be, let me write them here. Those will be W21, W22, and W23. And not just that, the third neuron will also have three weights associated with it. So then that will be uh, W31, W32, and W33. So these are the three weights which are associated with the third neuron. So overall, there are nine weights in this kind of layer which has three neurons. And let us see the outputs. So the first neuron will of course output f of w11 x1 plus w12 x2 plus w13 x3 plus b1. Similarly, the second neuron will also output f of w21 x1 plus w22 x2 plus w23 x3 plus b2. And similarly, the third neuron will output f of w31 x1 plus w32 x2 plus w33 x3 plus b3. So every neuron will have one single output which is associated with it. Correct? So this will be the output of that particular layer. And now your question would be, what is the advantage of stacking neurons in a layer? The main reason, or the real reason to understand this, can be found out when we look at the matrix. So if you look at the W matrix, it can be written as this: W11, W12, W13, W21, W22, W23, W31, W32, W33. Now, if you look at the matrix, every column of this matrix is the weights associated with the neuron. So this is weights associated with the first neuron, this is weights associated with the second neuron, and this is weights associated with the third neuron. Let's say W11 is 5, this is 5, and this is 5, which means that the first neuron places equal emphasis on all three features. So if we only had one neuron, only this information is available to us, correct? But now let's say the second weight is like this is 10, 0, and 0. So the second neuron has this information that pupil diameter is more important than the whisker length and the ear flappiness. Whereas if the third neuron has 10, 10, and 1, this means that not just the pupil diameter but the ear flappiness is also important. So you see, every neuron is encoding new information about the features. That's the advantage of having layers. When we have layers, multiple neurons can interact. Or another way of putting it is that we capture multiple relations between the inputs themselves. And that is an added advantage of really having these neurons in the first place. Having multiple neurons, we capture more patterns or more things in the data itself. Okay, so now let me do one thing. Let me again assume that all these weights are equal to 1. So currently what we have is that we have x1, x2, and x3. We have these three neurons and we have their outputs. And their outputs would be, so if all the weights are 1 and let's say bias terms are 0, so then this will be sigma of x1 plus x2 plus x3. This would be sigma of x1 plus x2 plus x3, and this will also be sigma of x1 plus x2 plus x3. Now your question would be, these are three outputs, right? How do I make the final prediction of whether it's a cat or whether it's a dog based on three outputs? That's a good question, and now we will add one more layer to this neural network, which will be our output layer. So now the neural network would look like this. These are the three inputs. This is the hidden layer, which is the first layer which we have. These are also called as hidden layers. And then we have an output. So up till now we looked at the weights in this part, But now we'll be looking at this part. So the output of these three neurons, which are these ones over here, will be the inputs to this particular neuron. And this will also have the summation, the bias, and the function, and then this will give the final output y. So then let me call these weights as W1 star, W2 star, and W3 star. So then y, which is the final output, is sigma, which will be the activation function of this neuron, W1 star into this output. So let me call this F1, this is F2, and this is F3. So these outputs are the inputs to this final neuron, right? So it will be W1 star F1 plus W2 star F2 plus W3 star F3. So we have already computed F1, F2, and F3. So let's plug in the values of F1, F2, and F3 here. So then what we get is y is equal to sigma of W1 star into sigma of x1 plus x2 plus x3. When I say sigma, it's sigmoid, plus W2 star sigma of x1 plus x2 plus x3 plus W3 star. So there should be B3 also, which is the bias with the final neuron. W3 star sigma of x1 plus x2 plus x3 plus B3. Now, if W1 star, W2 star, and W3 star are also equal to 1, and if B3 is equal to 0, my final Y will look like sigma of 3 times sigma of x1 plus x2 plus x3. This is my final Y. So this is my Y if my neural network looks like this, uh, where we have one hidden layer and one output layer. Whereas if you remember my Y when we only had one neuron, so if we only had one neuron, the Y was sigma of x1 plus x2 plus x3, correct? This is the difference between these two is that this is the formula when we have one layer, and this is when one neuron. Do you see the difference between these two? Here there is sigma of sigma, so it's a more expressive function where there is only one sigma here. Now, I want to illustrate this further because this really captures the point of why we need layers and why we need neurons. So, if you look at polynomial functions, such as if you look at x square dot x raised to 9, okay, and let's say we have a complicated data set which looks something like this. Let's say we have a complicated data set which looks something like this. Now, if you use only x, if you use only x to try to fit the data, you will only get straight lines, so it won't be very good. If you use x square, you might get some parabolic shape, still it won't be very good. But if you use x raised to power 9, so if you use all the orders up to this, so if you use x square, x to the power 3x raised to 9, so let's say if you have a function which is a1 x1 plus a2 x2 plus a3 x raised to 9, this will actually fit this complicated data in a much better fashion, because as the polynomial order increases, the function becomes more expressive. This is the idea of expressivity of functions. The more expressive a function is, the more complicated data it can capture. So consider these two functions. With one neuron, we already have a sigma, whereas with one layer, we have sigma of sigma. So this is like increasing the order in the polynomial, which means we are adding the expressivity of the function. We are improving the expressivity of the neural network. As we add more layers, it becomes sigma of sigma of sigma of sigma of sigma. So it is equivalent to saying the polynomial order is increasing and the neural network is becoming more and more and more and more expressive. That's why people use more layers, because the more layers you have, the more expressive the neural network becomes. Similarly, the more neurons you have, the more expressive a neural network becomes. So these are the two fundamental building blocks of a neural network. The neuron is the first fundamental block, and it has these three powerful functions of summation, bias, and the activation function. And the layer is the second building block of a neural network. So layer just stacks a bunch of neurons together. Okay. And what is the advantage of layers? First, we can capture multiple interactions between the features since we have more weights. And second, addition of more layers makes the neural network itself more expressive. So one way to think of neural networks is that it's just a function which is highly expressive. So let's say when someone gives you a neural network which looks like this, okay? Let's say when someone gives you a neural network which has three inputs. This is input. Uh, this is the first hidden layer with 10 units. This is the second hidden layer, 7 8 with 8 units, and let's say this is the final layer and this is the output. So let's say if someone gives you a neural network like this, it will have a huge number of weights, and it will have three inputs, and it will have one output. One simple way to think about this is that this neural network actually is just a function with a huge number of parameters. In fact, it turns out that this neural network, exactly this architecture, has 137 parameters. So instead of getting afraid of neural networks, think of it as just a complex function. That's one way to think about it. Second way to think about neural networks are that they are feature transformations. So if you take an input feature in three dimensions, you expand it to a huge number of dimensions, you take it through dimensions, and then you bring it down to one dimension again. Remember, in learning, we always like to take things in higher dimensions, learn their properties, train on them, and then bring it down to lower dimensions. So these are two ways of looking at neural networks. Let me just recap those. The first way of looking at a neural network is just that it's an expressive function. And the second way of looking at a neural network is that it's just a feature transformation. The final thing which I would like to leave you with is matrix representation. So it turns out that um, the same neural network architecture can be represented in a matrix formula. So let's say if you look at the neuron, right, or let's say we look at this example which we saw, and the output was three different things: f1, f2, and f3. This can also be written as these three outputs. So f1, f2, f3, f2, and f3 can also be written as w transpose x plus w0, where w is the weight matrix which we have already seen here. So w transpose will be w11, w21, or rather w11, w12, w13, w21, w22, w23, w31, w32, and w33. This is w transpose. X is just x1, x2, and x3, and w naught is just b1, b2, and b3. So if you do this multiplication and add this column, you will get this as the first row, you will get this as the second row, and this as the third row. The main point which I'm trying to make is that neural networks can be represented the functional formula in terms of matrices, and I'm going to quickly show you exactly for this neural network which has 10 units here, which has 8 units here, how the mathematical representation for this neural network looks like in terms of a matrix. So first, there is this thing called building blocks. So let's look at the first layer. The first layer, what it takes is input is x, then the weight matrix will be w, and the bias matrix will be w naught. Then it produces an output. So this will be w transpose x plus w naught, and then that will be fed to an activation function f. So f will operate on this thing, and then will produce an output which is a2. So this is z1 and a2. So this will be an output which will be passed on to this layer, this layer. Then it will be passed on to the second layer. So the weights will be w2, w02. Then the output will be z2. Then there will be this activation function f here again. Then the output would be a2. So a2 is the output of these neurons, which will be passed on to the final neuron. Then w3, w03, and then finally f, and then finally we'll get a3. So a3 is my y. This is the building block representation of this neural network. Let me try to explain to you what this means. So if you look at w1 and w01, these are the weight matrices associated with these neurons. So if you see this neuron will have let me draw it here. So this neuron will have three weights associated with it. This neuron will have three weights associated with it. So if you collect all these weights together, this is the weight matrix for that and the bias matrix. If you look at this block, so all neurons here will, so output from the first layer will be input to all these neurons. So this neuron will have all these as its weights. So it will have 10 weights. Similarly, this neuron will have 10 weights. So all these neurons together, if you put those weight matrices, that will be W2. And if you look at the final layer, this neuron will just have 8 weights associated with it. That is W3. And then the output of this neuron will be the final output, which is Y. So remember, F is the activation function here. And it can be same or different for the different layers. So the way this function is represented mathematically is that A3, which is the output, just looks like this: F3 of W3 transpose, F2 of W2 transpose, F1 of W1 transpose X plus W01 plus W02 plus W03. That's it. This is the output of this neural network, which is represented in matrix formula. So when someone gives you this neural network like this, don't be intimidated by it. Just remember that it can be represented in a simple mathematical formula like this. Now, if you try to compute the number of weights associated, let's do that. For the first neuron, there will be three weights here and one bias, right? So every neuron in this first layer has four weights, four learnable parameters, and there are 10 neurons here. So in the first layer itself, there are 40 learnable parameters. Let's look at the second layer. In the second layer, every neuron has 8 weights and one bias term, right? So every neuron essentially has 9, or sorry, every neuron here has 10 weights from the previous layer and one bias term. So it has 11 learnable parameters, and there are 8 neurons here. So overall, there are 88 learnable parameters. And here, there is one neuron who has 8 weights and one bias, so 9 terms. So if you add 40 plus 88 plus 9, there will be 137 learning parameters in this neural network. So this mathematical function which is shown here, that has 137 learnable parameters. And the simplest way to think of a neural network is that we have input, we have output, and we then use optimization procedures to learn these parameters and to optimize these parameters. That's all the game, that's all which neural networks does. And it's the whole game of neural networks is that we have a huge amount of learnable parameters and we have to optimize them for the problem which we are considering. I hope you understood what neural networks represent. From this video, I wanted to convey three things: the building blocks, which are the neurons, the layers, how the layers are stacked up together, the how does a neuron work, what are the three things within a neuron, and then finally, I wanted to show you how all of these things come together to give us the building block representation and the mathematical representation of a neural network in terms of matrices. I also wanted to show how every neural network is essentially a bunch of learnable parameters, and then which can be learned through procedures like gradient descent for any problem which you are considering. Thank you so much, and stay tuned for few further videos of this machine learning teach by doing project.